Whereas we can show that actually every stochastic matrix has a steady state vector, it's not necessary that they're unique. So here's an example. We take this stochastic matrix, which is, as you can see, is leaving the first state fixed and is flipping the second and third state. So that actually gives us that the vector 1, 0, 0 is a steady state vector. It also shows us that a vector which is nicely distributed between the second and third states is a steady state vector, and indeed a combination of those two gives steady state vectors. And with a little bit of calculation we can actually see that any vector of this form, A, B, B, such that the A's and B's greater than 0 and that they add up to 1, A plus 2B is equal to 1, so we get a stochastic, so we get a probability vector. These will be steady state vectors for the above transition matrix, P actually. So what we'd really like is to have some sort of condition on our transition matrix such that the transition matrix has a unique steady state vector Q, and that the Markov chain associated with T converges to the steady state solution independently of the initial condition, initial state x0. For these sorts of Markov chains we will easily predict the long-term behavior. Now it turns out that there is actually a large set of stochastic matrices for which the long-range predictions are possible, and these are called regular stochastic matrices. So let's have a definition of regular. So what we want is actually a transition matrix, or some power of it, which ensures that we have a positive probability of going from any state to any state. So the actual definition is a stochastic matrix T is regular if for some matrix power Tk contains only strictly positive entries. Another way of saying that is that the transition matrix of a Markov chain is regular, then for some k value it is possible to go from any state to any state, including remaining at the current state, in exactly k steps. So taking our simple weather example, our original transition matrix is of this form. It has a 0, so that looks like it might be a problem, but if we even just look at t squared, we see now that all the entries are strictly positive. So this transition matrix is a regular stochastic matrix. But not all stochastic matrices are regular. So here's a very simple example. We have a situation where we're flipping between two states. If we calculate t squared, we get that that's the identity, but there's still 0 states to deal with, here and here. And then if we calculate out t cubed, we get back to t. So no matter how many powers of t we calculate, we'll still have 0 entries. So this is an example of a matrix which is not regular. Okay, so now we can write this result down as a theorem. Now let's suppose we have a transition matrix which is a regular stochastic matrix. We just defined what regular is. Then we have this really nice result that we have a unique steady state vector, and what's even nicer in a sense is that the entries of the steady state vector are strictly positive. So there's definitely a positive probability of going to any of the states. Now, in terms of actually finding this steady state solution, one way we can do this is that if we start off with any initial probability vector, so let's say x0, then we apply our transition matrix, so in this way. Then, as we let k go to infinity, the Markov chain entries, the xk's, converge to the steady state solution as k goes to infinity. And alternatively, in terms of just matrix multiplication, the limit of t to the k operating on any initial condition, x0, will converge to the steady state solution. So we know that we have a unique steady state solution if we have a regular stochastic matrix, and in a sense we have a nice iterative way of actually approximating it. We can actually make another observation, so let's have a look at this part down here. So we know that the T matrix is made up of columns, P1 up to Pn, and if we take our initial condition as being one of the basis vectors EI, something with 1 in the ith position and 0 everywhere else, then we actually know that T operating on EI will actually just give us the ith entry, ith column of T. So by using an EI as an initial condition, we have a way of extracting out columns of a matrix. So pushing that along, if we want to get the ith column of TK, we just have to calculate xk, which is tk times x0, which in this case will be tk times e to the I. So the upshot of that is that, and the upshot of our theorem is that t to the k operated on EI actually converges to our steady state vector q, and that's true for any I. So essentially we get the conclusion that the full matrix t to the k, each of the columns of t to the k approaches the limiting vector q. So if we were to multiply out our t to the k for large values of k, it should essentially look like a matrix with identical columns, and the identical columns will be q, or at least an approximation of q. Okay, so let's do a simple example. Let's suppose we have a transition matrix, little 2x2 transition matrix, maybe representing the movement of population from city to suburbs, maybe movement on 2 levels of Avery, whatever. Anyway, so the main problem we want to do is calculate a steady state vector associated with t. So essentially we want to calculate an x so that t of x equals x, and that is the same as t minus the identity times x is equal to 0, which is the same as finding the null space of t minus I. So that's our calculation. So let's just do that. So there's our t minus I, and there is the reduced form. Now, basically, we get that x1 is going to have to be equal to 5 over 2 times x2, and x2 is free, so that's easy. So our vector is of the form x1, x2 is equal to x2, free variable, 5 on 2 times 1. Now we have to actually calculate the x2 so that it's actually a probability vector. So what we need to do is essentially calculate the right sort of factor, x2, so that the vector entries add up to 1. So what do we need for that? Essentially we need that x2 times 5 on 2 plus x2 has to equal 1. So that's the same as saying that 7 on 2 x2 is equal to 1. So that tells us that x2 has to equal 2 sevenths. I'm sort of running out of space here, but that would then imply that the corresponding vector that we need, so I might change the colour, so the corresponding vector that we need will actually be x2, this particular x2, times this particular vector here. So that gives us a vector which is 5 on 7 and 217. And as you can see, the entries add up to 1. They're positive, and that will be our steady state vector. By the way, we actually had an alternative solution which is special for this 2 by 2 case. This matrix here can be written in this form. Obviously the P has to be 0.2 and the Q has to be 0.5, and then our previous result for 2 by 2 transition matrices told us that the steady state vector was just given as 1 over P plus Q multiplied by the vector QP, and of course in that case we get exactly the same result. So let me just finish up with one more calculation. Let's consider the weather example. So if you recall, the transition matrix for our weather, fine, cloudy, raining, was given by this matrix here. Now it's not a 2 by 2 matrix, so we don't have a special way of calculating the steady state solution. So we just have to go back to the simple calculate the null space and then normalize the vector so that the entries add up to 1. So let's just put the calculation. Let's just calculate. So we need to calculate the matrix T minus I. So there it is. We're just taking the entries and we're changing these diagonal terms by the -1. Then we row reduce, and we would expect to get one free variable. This is because it's a regular matrix. We expect there to be a unique solution, and that will be obtained by taking the one free variable and choosing the particular value of the free variable to make it a probability vector. So that's a bit of a test. When you do if you've got a regular matrix and you do the calculation of null space, you should only get one free variable. All right, so that's true here. So we can obviously calculate the x1 in terms of the free variable. So that's 1/2 x3. x2 is equal to x3, and x3 is equal to 1. Oh, sorry, x3 is equal to x3. And of course then we get that the vector x1, x2, x3 is equal to x3 times 1/2, 1 and 1. And of course that means that our null space is spanned by this vector here. So that's what we get there. And then we just normalize it by choosing an appropriate value for x3, and that gives us the steady state solution for this little bit more difficult 3 by 3 example. So we expect that for 1/5 of the time, 20% of the time, this land of Oz or England will have a clear sky, and 2/5 of the time, 40% of the time, it'll be cloudy, and 40% of the time it'll be rainy. So that's the process you need to do to calculate the steady state solution, the long time behavior of a Markov chain. In the notes, you'll actually see there's another example, and I'll let you go through that yourselves. But I hope you've seen that the Markov chain method is really quite powerful at modelling quite a range of different things. And in the assignment, we'll actually see that a similar Markov chain idea can be used to actually measure the importance of web pages. So hope you have a good time doing that assignment question.